So, good morning. We've been looking at medical imaging, and today's task for the single lesson and the double lesson is really to go through some of the some exam questions. What I'm going to do is I'm going to do a walkthrough, and then your task afterwards is going to be to continue to revise that medical imaging topic, and also make sure that you can have a go at doing the same questions yourself, having seen the walkthrough. I'd like you to do it. Hang on, just got Ikenna has just arrived, so I'll just admit Ikenna. So what I'd like you to do is to watch and listen, and then have a go at the exam questions without just sort of copying what I do. So I'm going to show you how to do it, then you're going to have a go at doing it. That's the idea. It's called a walkthrough. So the first part of the question on the pack that I've sent you is looking at ultrasound waves and other medical imaging like MRI. So we start off with some ultrasound questions. The first question, obviously paper 4, the questions nearly always begin with a definition question. This first question, by reference to ultrasound waves, state what is meant by acoustic impedance. This is a straight definition that actually links to a formula. So it's literally the density of the material multiplied by the speed of the sound wave. You can say it in words, you can say it's the product of density and speed of sound waves, but basically that is more or less your answer. It's a 2-mark question, so maybe they want a bit more. Well, maybe we should actually be a little bit more specific. It's going to be the density of the medium multiplied by the speed of sound waves in the medium. Okay, the first mark given by exams is by an examiner would be for that straight sort of formula. The second mark would be for the slightly more precise answer of saying it's the density of the medium and speed of sound waves in the medium. On to the next question. You've got an incident ultrasound waves hitting, going through 2 materials with impedance of Z1 and Z2. And you have to explain the importance of the difference between Z1 and Z2 for the transmission of ultrasound across the boundary. Well, basically, the idea is meant to be that if Z1 minus Z2 is large, so if Z1 minus Z2 is large, then you get mostly reflection, or most of the waves are reflected. And you then need to sort of qualify it by saying that what happens if it's small, or Z1 minus Z2 is small, then you get most of the wave is transmitted or goes through. And that's worth 1 mark. So that's worth 1 mark there. That's 1 mark there. So but it's a 3-mark question, so you need something a little bit more precise. Well, basically, you would quote the formula that you have in your book. It would be the reflection coefficient is actually, well, it's going to be Z1 minus Z2 over Z1 plus Z2 squared, because it's intensity. And that's basically it. So the 3rd mark is really for the more precise answer. The last part, it says ultrasound frequencies as high as 10 megahertz are used in medical diagnosis. State and explain one advantage of the use of high frequency ultrasound compared with lower frequency ultrasound. So basically, remember, if you've got a higher frequency, well, what that does, that implies a short wavelength. Okay, so if you've got a high frequency implying a short wavelength, then if that's the case, then you know you'll get better resolution. That's a simple answer. Okay. Okay, that's basically it. You got 1 mark for the fact that that it creates a short wavelength, and then another mark for qualifying it and saying that the shorter wavelength gives you better resolution. That's why you can read small text under blue light, but not very well under red light, because red light's got a longer wavelength. The next part of the next question is all about X-rays. So I'll set you then a question on X-rays. It says, explain how the hardness of an X-ray beam can be controlled by the accelerating voltage in the X-ray tube. Well, the idea is, of course, that the accelerating voltage controls the speed of the electrons. Okay, and that in turn controls the kinetic energy. The next part of the question, the next part of your answer, because it's 2 marks, you then need to just qualifying it by saying that the kinetic energy of the electron controls the X-ray photon energy. Simply because the hardness of the X-ray beam is dependent on the energy of the photons, because the higher frequency, higher energy photons are basically a harder beam. The next part is all about attenuation. When you're going through this, you can think about these sort of textbook definitions. Okay, so this one here is a textbook definition. So the attenuation literally means a loss of intensity. So when we say a beam of X-rays is attenuated, we mean its intensity is reduced. Explain why the expression applies only to a parallel beam. Well, if you don't have a parallel beam, then that's going to affect the intensity as well. So the intensity reduces with distance for we're saying non-parallel beam. We assume it spreads out. If you think about it, if the beam spreads out, if your beam is spreading out, you know that you've got a certain amount of energy per sort of unit area there. If you've got the beam spreading out, obviously you've got the same energy being applied over a larger area, means the intensity is going to be less. And for the last part is just a straight calculation, pretty simple to do. The best way to do that simple calculation is just to look at what values you're given. It wants the fraction of I over I naught for bone over the fraction I over I naught, the attenuation of the X-rays through soft tissue. You're given the thickness, okay? So those two values are going to give you X. So we're looking at using the same formula. If you look at the top here, you're given this formula. You're going to use this. So the intensity through the bone is going to be E to the power of minus mu, which is the attenuation coefficient, times x1, so that would be for bone, over E to the power of minus mu to x2. We're just using that formula. So then you just substitute. Are we given the linear attenuation coefficients? Yes, we are. So for bone, 0.95. So that's E to the power of 0.95 multiplied by the thickness of the bone, which is 2.5 centimeters, divided by E to the power of minus the attenuation coefficient of the, oh no, have I done something wrong here? Yes, I have, because bone is there's 2.9, not 0.95. 2.9, that's 0.95 multiplied by the thickness of the tissue, which is 6 centimeters. Okay, now you probably noticed it's in centimeters here, but then the attenuation coefficient is also in centimeters to the -1. So if you got it, say, in meters to the -1, then the thickness would have to be in meters as well. The units would have to be, would have to correspond. Once you've done that, it's a straight calculation. You do the calculation and you end up with an answer, which I'm not going to give you because I want you to calculate it. I want you to have to go through and calculate it. So I'm not going to give you the answer there. So question number 3, your favorite kind of question. Of course, I'm being a little bit sarcastic there, but it's a particular type of question that I know not everyone likes, which is the big sort of explanation questions, and it's worth 8 marks. So there are 8 things you've got to say. So what's it asking? It says explain the main principles behind the use of nuclear magnetic resonance imaging, MRI in other words, to obtain information about internal body structures. So you have to think about what actually how it actually works. Well, the idea is you start off with a strong magnetic field. Well, let's be precise, a strong uniform magnetic field. We know that that makes all the atoms point the same way. Well, we don't want to say point the same way. We want to be a bit more precise. So we say it causes nuclei to, well, it's the idea that they rotate. So they rotate about the same axis. That's what I really mean. That's what I really mean by making the atoms point the same way. Okay, so that's the first principle of it. And then you have an oscillating magnetic field. And from your reading, you should have an idea that it should be in radio frequencies. So an oscillating magnetic field, you could even say it's weaker than the uniform field, but basically that's kind of taken as read. So the oscillating magnetic field, we say that if it's at the resonant frequency, well, what's the resonant frequency of an atom? We call it the Larmor frequency. At the Larmor frequency, causes the nuclei of the atoms to resonate. Okay. Okay. And we know that the nuclei then emit a radio frequency pulses. Okay. And we know that the Larmor frequency changes with position. And that allows the position of the nuclei to be determined. Okay. That's basically it. So this would be an 8-mark question. So if I look at my mark scheme, the idea is you've got a strong uniform magnetic field. Just the mention of that is worth 1 mark. And the idea that it causes the nuclei to rotate about the same axis is 2nd mark. An oscillating magnetic field, believe it or not, if you just mention that, that's worth 1 mark. And the idea that it's at or around the Larmor frequency causes the resonance. In fact, you get a mark for saying it causes resonance, so that's 5 so far. Then the nuclei then emit the radio frequency pulses, that's worth 1 mark. And you then say that the Larmor frequency changes with position, allowing position to be determined. That's 1, 2, 3, 4, 5, 6, 7, 8. That's how you get the 8 marks. Notice I've only used about half the space just by being very precise about what it is I want to say. Okay. Question number 4, what is meant by the hardness of an X-ray beam? Again, you've got to think about what that actually means. It was mentioned before in the previous question, in a previous question. The hardness, remember, is the kinetic energy of the photon energy of the X-rays, which dictates the penetration of the beam. So it's the idea that the hardness is the energy of the photons okay, so it's the energy of the X-ray photons which then dictates the penetration. High energy implies the greater penetration of the X-rays. Okay, that's basically it. It's only a 2-mark question. That's the 2 particular parts. One for linking it to the energy, the photon energy of the X-rays, and then saying that if you've got a higher energy or harder beam, it has a greater penetration. Okay, so how is the hardness of the X-ray beam increased? We know that that is a greater accelerating voltage of the electrons. We know that from the previous question, so yeah, that's easy. Greater accelerating voltage of electrons. Okay. And again, you've got a very, very, very similar question to the last one. Only this time you're not given the formula, but you do know it. You know, the intensity transmitted through the bone. You want to work out that ratio. So the intensity transmitted through the bone is going to be e to the power of minus mu for the bone, which is 2.9 times 1.5. Again, they've got it in centimeters and centimeters to minus 1, so we don't have to worry about the unit. And then e to the power of the attenuation coefficient of 0.95 for tissue or muscle, multiplied by the thickness, which is 4 centimeters. And that then comes out, and I'll leave that for you to do. Okay, I did say it would be quite quick. I'm not going to spend much more time on that. So what I would like you to do now is sort of continue your revision. So make sure you revise, make sure you've done some revision of X-rays, MRI scanning, and ultrasound. Although it doesn't feature in the questions, it's worth making sure you understand about how a CT scan works. Okay, so that's what I'd like to do. First of all, your next task is again rewatch this this video. Just watch the video again for a second time, and then for the third part is then do the questions without the video. You need to do it without the video, because what I want you to do is to watch the video, watch the techniques, watch the points, listen to the points that I make, and then do that from what you can remember from what I've shown you. So I'm going to switch your microphones on so that if you've got any questions you can ask. So bear with me for a second while I do that. So has anybody got any questions?
No, sir.
Nothing.
No, you're all okay? You reckon you can do that?
Yeah.
Okay, we'll give it a go. I'll post the video up on Show My Homework as soon as I've got it converted. So that'll be up within the next sort of 15 minutes or so. Is that okay?
Yeah.
Okay, right. Thank you very much for attending the lesson, and I'll see you next time.
All right.
Have a good day.